In this video, I am going to discuss about spin-orbit interaction. This particular spin-orbit interaction, uh, one must understand while studying the spectra of one valence electron system. So, the optical spectra of alkali elements show a fine structure splitting. Fine structure splitting means some of the lines, even though with low resolution spectrometer, they appear to be a single line, but when you observe them through a high resolving power spectrometer, you will find that these lines are having fine structure. So they are doublets. Energy levels such as P, D, F, G, etc. are doublets in the spectra of alkali elements, and this is due to spin orbit interaction for optically active electron. So optically active electron means the electron which is in the last subshell, or what we call as valence electron. So this valence electron, as I have explained already, that is only contributing into the total angular momentum of an atom. Therefore, the actual atomic states will be defined by this last electron, which is called as optically active electron. And a typical interaction which we are going to study in this particular video, which is known as spin orbit interaction. So let us see now what is this spin orbit interaction, which is responsible for this fine structure in the spectra of alkali elements. So the kind of interaction one can explain as the coupling between spin magnetic dipole moment of an electron and the internal magnetic field of the atom. You can use this word coupling or interaction parallelly. So coupling or interaction between the spin magnetic dipole moment. So spin magnetic dipole moment, you know that because of the spin motion in vector atom model, we have seen this particular explicit property of the electron in an atom, that they have a spin. So this electron spin, because of the electron spin, there will be a spin magnetic dipole moment associated with this electron, and because of the orbital motion of the electron, there is internal magnetic field of an atom. So this spin magnetic dipole moment in presence of internal magnetic field, so there will be interaction of these two. So since the internal magnetic field of the atom is related to the orbital motion of the electron, and that means the electron's orbital angular momentum, this interaction therefore is called as spin orbit interaction. So the interaction between spin magnetic dipole moment and internal magnetic field. So internal magnetic field is because of orbital angular momentum. Therefore, this interaction is called as spin orbit interaction. This is called as spin orbit interaction. Now this interaction, spin orbit interaction, it is relatively weak interaction. This is relatively weak interaction, and this is responsible for the fine structure of excited state of the one valence electron system. So as an example of one valence electron system, here the alkali element we are going to discuss is sodium. So we are going to study the spectra of sodium. So whatever the fine structure observed in the alkali elements, in the spectra of alkali elements, that is due to this weak interaction, spin orbit interaction. Now the interaction energy, it was calculated by Pauli, Darwin, Dirac, Gordon and others on the basis of quantum mechanics. And this particular derivation we are going to discuss here in this particular video. So a lot of quantum mechanical terms are related here. So I will assume that you are familiar with some of this term, and even though if you are not familiar with these quantum mechanical terms, but just the needed explanation I will give you at that particular point. So the interaction energy, this spin orbit interaction, the interaction energy is defined as the change in kinetic energy of the system due to precession of an electron around the field. So the internal magnetic field of an atom and the spin motion of the electron, so there is an interaction, and because of that there is a change in kinetic energy of the system, and this change is because of precession of electron around the field. So this precession earlier also we have discussed, so let us consider this particular precession once again. So consider an electron of mass m and having charge minus e, moving with a velocity v in a circular Bohr orbit of radius r. So suppose this is the circular orbit, Bohr orbit, having a radius r, and this is the position of the electron having charge minus e, and this vector v represent the velocity of the electron in an orbit. Okay, so this particular motion, because of this particular circular motion, the current will be developed. So you know that whenever a electric charge is in motion, we say that there is a electric current. So here electron is in circular motion in this particular direction. So there will be current I. A current I will be set up here. So this particular current, because of the motion of the electron in a circular orbit, you can define as I is equal to E upon T. What is E? The charge. Okay, electron charge, electronic charge, and T is the time period in this circular orbit. So you know that current usually it is defined as the rate of flow of the electric charge. Okay, so electric charge is the electron charge E here, and the rate, that means how much time it will take to complete the one cycle, so that is the periodic time. So E upon T, that will give this value of the current I in this circular orbit. So T is the period of revolution of the electron. So if V is the speed of electron, then you can just say the T you can define as the periodic time T. So by using the definition of the periodic time T, so time taken to travel this distance 2 pi r. So for circular orbit, the circumference is the distance travel with the velocity v. So 2 pi r upon v, that will be T. So if you substitute here the current in the earlier equation of current, so I will become EV upon 2 pi r, because earlier we have defined that I is equal to E upon T. T is in the denominator. So T is actually 2 pi r upon v. 2 pi r is the circumference and v is the velocity of the electron. So that will define the time taken to complete one particular orbit. So that is period. So the equation will become I is equal to EV upon 2 pi r. Now the for a current I in a loop of area A, the magnetic dipole moment is given by the equation mu I, that is equal to I into A, that is equal to, so I the current into A. A is the area of this loop. So here we have circular path. So the area is pi r square. Area is pi r square. So I, this particular value of I, and the area pi r square. So the magnetic dipole moment mu I, that will be IA into EV upon 2 pi r into pi r square. So this is the magnetic dipole moment. So mu I, that is equal to EV r. So this pi and one of the r will get cancelled. Mu I, that will be equal to EV r upon 2, and that you can just multiply and divide by m both in numerator and denominator. It will be transformed as E upon 2m into mvr. E upon 2m into mvr. So mvr, you know that the in circular motion, that is the angular momentum PL. mvr, that is equal to the angular momentum PL. So this particular angular momentum PL you can substitute here in this particular equation. So mu L, this is actually mu L, okay. So that is equal to E upon 2m into PL. So here if you substitute, this is not I, sorry, this is L, suffix L. So mu L, that is equal to E upon 2m into PL, where PL is the angular momentum. Now see here, in this particular diagram, we have shown PL, this is the angular momentum because of the circular motion of the electron, and this is mu L, that is the magnetic dipole moment. So these two vectors are opposite, in the opposite direction. Why? Because the electron, the charge, because of this charge E, this charge E is negative. So its magnetic dipole moment mu L is anti-parallel to this angular momentum vector PL. So this is shown in this particular diagram. Okay. So the quantity mu L specifies the strength of the magnetic dipole. Okay. It specifies the strength of the magnetic dipole. Okay. So the strength of the magnetic dipole mu L, it is product of pole strength and the pole separation. You know that earlier in magnetism, electricity and magnetism, you may have studied this, the magnetic dipole moment. So it is product of pole strength and the separation of the two poles. Okay. So mu L, that is equal to E upon 2m into PL, or if you take this PL to the left hand side, so mu L upon PL, that is equal to E upon 2m. So in this relation, mu L is equal to PL into E upon 2m, you can write it as, so PL you can substitute here as LH upon 2 pi. Okay, because this angular momentum is quantized, it is integral multiple of L. So it is, according to quantum mechanical concepts, it is quantized. So it is LH upon 2 pi. So if you substitute here PL in this particular equation, this equation here, so L into H upon 2 pi, so this will become L into EH, 2 into 2, 4 pi m. Okay, so L EH upon 4 pi m, because PL is equal to L H upon 2 pi. Now the quantity EH upon 4 pi m, this particular quantity in this relation, this is representing the smallest value of mu L, this magnetic dipole moment. It is the smallest value of the magnetic dipole moment. Therefore, it is used as a unit for measurement of the magnetic moment of the particles. So it is known as Bohr magnetron. It is known as Bohr magnetron. And if you substitute the values of the E, H is Planck's constant, m, that is mass of electron, this value comes to be 9.27 into 10 raised to minus 24 joule per Tesla. So that is the value of Bohr magnetron, and it is used as a unit for measurement of magnetic moment of the particle. So the motion of this magnetic moment of a particle about the direction of magnetic field, that is known as the Larmor precession. This is known as the Larmor precession, and this Larmor precession is important because we are going to define the spin orbit interaction. The change in kinetic energy of this system is because of this Larmor precession. So what is that? It is because of the motion of the magnetic moment of a particle about the direction of magnetic field. So this is the Larmor precession. Now an electron moves in the electric field E of the nucleus with a velocity v. So when the electron is orbiting about the nucleus, so nucleus has positive charge, so it has its own electric field. So the electron is moving in the electric field E with a velocity v. So the motion of the electron experiences a magnetic field given by H is equal to E cross V upon C square. So this moving electron that experiences a magnetic field which is given by H is equal to E cross V upon C square. So the electric field here, it is due to the nucleus, and it is given by this equation E is equal to JD upon in bracket 4 pi epsilon 0 r cube into vector r. So in a vector form, this electric field is defined like this: JD upon in bracket 4 pi epsilon 0 r cube into this vector r. Okay, so therefore if you substitute the value of E here in this relation, so what you get here is H, that is this particular magnetic field will be given as ZE. So this ZE upon this ZE upon C square r cube, this C square and this particular r cube, into r cross v. So this vector r and this vector v. So cross product of these two divided by 4 pi epsilon 0. This 4 pi epsilon 0. Okay, so if you just rearrange the term, so what you get here, jd upon c square r cube, and if you multiply by m, multiply and divide by m, so m c square r cube, and this m we have taken here, r cross mv upon 4 pi epsilon 0. So according to Bohr quantum condition, the orbital angular momentum is r cross me, that is equal to L star h upon 2 pi. So this r cross mv in this relation you can replace by L star h upon 2 pi, where L star, according to quantum mechanical conditions, this L star, the magnitude is given by under root of L in bracket L plus 1. So therefore if you substitute this value here, in this earlier relation, we have seen this value, so r cross m v bar. So if you substitute L star into h upon 2 pi here in this equation, so that equation will become h will be equal to L star h upon 2 pi jd upon mc square r cube into 1 upon 4 pi epsilon 0. Okay, so this field, in this field the magnetic moment undergoes Larmor precession. So we have defined earlier the Larmor precession. Now this Larmor precession around the field direction, this magnetic field. Okay, so the angular frequency of Larmor precession is given by omega L is equal to this h, magnetic field strength h, into E upon m. So this Larmor precession, angular frequency of Larmor precession is given by omega L is equal to h into, h means this magnetic field, so magnetic field strength h into E upon m. So this is the product of field strength and the ratio of magnetic moment to the mechanical moment of the spinning electron. So this ratio E by m is the ratio of magnetic moment of the to the mechanical momentum of the spinning electron. Okay, so there exists a relativistic precession of an electron. So along with Larmor precession, there is also a relativistic precession. So this relativistic precession is in the opposite direction to that of the Larmor precession. So the angular velocity of the relativistic precession is half of Larmor precession. So therefore, the resultant angular velocity is given by, so you can see here the relativistic precession omega r, angular frequency of relativistic precession omega r, that is equal to half of the angular frequency of Larmor precession. Therefore, and it is in opposite direction, so there will be a subtraction rather in terms of vector. So the actual angular frequency, it will be h into E upon 2m. So the resultant angular velocity is vector sum of the two. So h upon h into E upon 2m. So you can see here omega, final omega is h into E upon 2m. Or if you substitute the value of h, earlier we have defined, if you see this value of h, so if you substitute here h, so omega will be equal to 1/2, this 1/2 I have taken here, 1 upon 2. Okay, so h, so 1/2 L star h upon 2 pi jd square upon m square c square r cube into 1 upon 4 pi epsilon 0. So the spin orbit interaction energy delta ws, it is given by the relation delta ws is product of angular velocity, this angular velocity, resultant angular velocity, into projection of the spin angular momentum vector on the orbital angular momentum vector L star. So if you take the projection of the spin angular momentum vector S star on the orbital angular momentum vector L star and multiply with angular velocity, you will get the spin orbit interaction energy. That means the change in kinetic energy of the one valence electron system. Okay. So delta ws, wls, this ls suffix you can see here. Okay, delta w, it represents the spin orbit interaction energy, and this ls, l for orbital motion, s for spin motion. So spin orbit interaction, in order to represent the interaction energy of spin orbit interaction, this l and s, these suffix are used. Okay, so the omega into s star. So this omega here, interaction, angular velocity of this interaction. So the omega into projection of spin angular momentum on L star. So that is S star into h upon 2 pi into cos of L star S star. So this is the projection. This second term represents the projection of the spin angular momentum along the orbital angular momentum vector. So S star into h upon 2 pi into cos of L star S star. Okay, so this interaction energy delta WLS, if you substitute the value of omega here, this value, so that will be Z E square upon 2 m square c square into h square upon 4 pi square r cube into 1 upon 4 pi epsilon 0 into L star S star. This you can see S star cos of L star S star, and this L star here you can see this L star. So therefore L star S star cos of L star S star. Okay, so the radial distance R, radial distance means the distance of electron from the nucleus. So this distance is function of what? Z, atomic number Z. So in Bohr's theory we have seen that. So the radial distance R is function of Z, then the principal quantum number N, and the value of L, and it changes continuously in a given state. It changes continuously in the given state. So L, actually you know that this orbital quantum number and the value of L represents actually the shell, also small value, subshell. Okay, so the interaction energy is very small as compared to total energy of the system. Therefore we need to consider average value of this interaction energy. Okay, delta WLS. That means here, since it is function of R, mostly function of R, so here we have R cube. So we must consider here this particular function 1 upon R cube. So interaction energy is mostly function of 1 upon R cube, and this R is continuously changing in a given particular state. Therefore the average value is considered. And one of the important theory in quantum mechanics, perturbation theory. So according to perturbation theory in quantum mechanics, the average value of this quantity 1 upon R cube, it is represented by like this, average value of 1 upon R cube. It is given by Z cube upon A1 cube N cube L in bracket L plus half into L plus 1. And if where A1 is the radius of Bohr's first orbit, and it is given by the equation A1 is equal to h cross square into 4 pi epsilon 0 upon m m0 or m, you can just say raised mass of the electron, m0 into E square, where h cross is h upon 2 pi. Okay, so m0 or m, I have used the same term here. Instead of m0 you can consider it m also. Okay, so not necessary to show this 0 which represent the rest mass of the electron. Okay, therefore if you substitute these terms, the average value, then this A1, so let us substitute in the earlier equation of this interaction energy delta WLS. So the equation will become Z raised to 4 E square h cross square upon 8 pi square m square c square into L star S star cos of L star S star upon this value of A1 cube. Here you can see A1 cube. So therefore this A1 cube, h cross square 4 pi epsilon 0 upon 4 pi square, this me square bracket cube into n cube L in bracket L plus half into another bracket L plus 1 into 4 pi epsilon 0. So this particular equation we have just defined here by substituting A1, this average value of 1 upon R cube in the earlier equation. Okay, so now let us just simplify these terms, and after simplification and just cancelling some of the terms, this delta WLS will take a form of like this equation. So it is 8 pi raised to 4 Z raised to 4 me raised to 8 L star S star cos of L star S star divided by c square h raised to 4 n cube L in bracket L plus half in another bracket L plus 1 into 4 pi epsilon 0 bracket raised to 4. Okay, so if you simplify this, you will find that it is equal to this particular equation. Okay, so now in this particular equation we shall substitute two constant here. Okay, so one constant r, that is the Rydberg's constant, that is the Rydberg's constant. So 2 pi square m e raised to 4 upon ch cube into 4 pi epsilon 0 bracket square, and uh, alpha square, that is equal to 4 pi square e raised to 4 c square h square 4 pi epsilon 0 bracket square. So this is the Rydberg constant and this is the fine structure constant. Okay, so therefore if you substitute this r and alpha for these terms in the earlier equation, so the equation will be simplified in this manner. So delta WLS, the interaction energy, is r alpha square ch z raised to 4 into L star S star cos of L star S star into n cube L in bracket L plus half in another bracket L plus 1. So now if you consider this precession here, in a field free space, L star and S star precesses around their resultant J. So this is suppose L star and this is S star, they will precess around this resultant J. So the resultant of this two L star and S star is suppose J, because J represent the total angular momentum, S spin angular momentum, L orbital angular momentum. So these two, their resultant will this total angular momentum. So these two vectors S star and L star, they will precess about the direction of J star. That will form a cone. That will form the cone. So if you apply the cosine law in this particular vector diagram, so using a cosine law, this J star square, that will be equal to L star square plus S star square plus 2 L star S star cos of L star S star. And if you simplify this equation further, you will find that so if you take these two terms on the left hand side, so J star square minus L star square minus S star square divided by 2, so that will be equal to L star S star cos of L star S star. Okay, so because we have this term here L star S star cos of L star S star, so from this vector diagram and by using cosine law, we have defined this term as J star square minus L star square minus S star square divided by 2. So let us substitute in this particular equation. So the interaction energy delta WLS, see now average interaction energy, because we have substituted the 1 upon r cube, average value of 1 upon r cube. Therefore this bar represents the average value. Okay, so r alpha square ch into z raised to 4 upon n cube L in bracket L plus half in another bracket L plus 1 into this value. Now just we have defined from cosine law, so J star square minus L star square minus S star square divided by 2. Okay, so R, as I have earlier told you, that is the Rydberg constant, and alpha square is the fine structure constant, because the spectra of locally elements that has the sum of the spectral lines has a doublet structure, that means they are having fine structure. So it is defined by the quantitative manner. This is defined by this constant alpha square. So this interaction energy is sometimes also called as term shift. So in terms of spectroscopy, it is called as a term shift. Okay, so this term shift value is nothing but the change in kinetic energy of the system. That means the interaction energy. And dividing this particular equation by Hc, you will what we get is this particular value delta gamma ls. Okay, the term shift that can be defined in this manner. So that will be minus r alpha square z raised to 4, ch will get cancelled here, upon n cube L in bracket L plus half into another bracket L plus 1 into this particular term J star square minus L star square minus S star square divided by 2. Okay, so this minus sign you can see here. So this negative sign indicate the convention that term values are measured from series limit downwards. That means the higher values are placed normally in the downward direction, and we start on the scale from the lower values at the top. So this delta gamma ls, which represent this term shift, that is equal to minus gamma. So this entire value you can just consider as gamma, so it is minus gamma. So this gamma factor indicates the spin orbit interaction energy, or it is also known as term shift, and therefore this this gamma is equal to A L star S star cos of L star S star. So what is A here? So if you consider the earlier relation here, so this is actually L star S star cos of L star S star from cosine law. If you consider the earlier, so this value will be A into that L star S star cos of L star S star. So therefore in this particular case, this A is the constant value here. Okay, so gamma is equal to A L star S star cos of L star S star. So the gamma is equal to A. So this can be represented as also by J star square minus L star square minus S star square divided by 2, as we have seen earlier from the cosine law. So where A, as I have mentioned, this is a constant. Okay, in spectroscopic term, R alpha square Z raised to 4 divided by n cube L in bracket L plus half into L plus 1, and its dimensions are centimeter inverse. Okay, so just like a wave number, this also has the dimensions centimeter inverse. So the term value gamma measures separation from the hypothetical center with the term value gamma 0. So what is gamma representing? Term shift. So separation from the hypothetical center with the term value gamma 0. So you can represent this as, thus separation in terms of value due to spin orbit interaction is this gamma j, that is equal to gamma 0 minus gamma. So this separation between the hypothetical center, the actual separation will be represented by this term shift gamma. So the gamma j, that is equal to gamma 0 minus gamma. So for the alkali spectra, it is observed that what is this gamma? So the separation increases with increase in atomic number. So as we go to the higher atomic number of the alkali elements, it is found that the separation, that means gamma, because of the spin orbit interaction, that will go on increase as the atomic number increases. Now the separation found to be decreasing with increase in principal quantum number n. So for the same alkali element, if you go to the higher state, that means with a higher value of the principal quantum number n, then it is found that the separation decreases. Then another important conclusion that is observed in the spectra of alkali elements, that is the separation decreases with increase in L. The separation decreases with increase in L. So L value, as you know, that it is representing the particular subshell. So as you go to the higher value of L, the separation will further decrease. Separation among the fine structure of the lines, remember. So next in the next topic, actually we are going to study the actual spectra of sodium, which is one of the important alkali element, and there we will see these actual facts observed about. So these are common facts observed for the alkali spectra. So for sodium also we will observe this particular fact in the spectra, and from that one can just define these are the characteristics of the alkali spectra.